Hello, Caymans. Mr. Eicher here, bringing a 5.5 lesson on radical operations to you. Radicals are radical. We have several problem types under this section, so this might be the first of 2 or 3 videos. But let's start with the top. The following radicals are not simplified. What's wrong? Well, as you can see on the first two, there are factors that you can actually pull out of the square root or the cubed root. So to be simplified means that there are no more factors that you can take the nth root of. On this one, we have a radical in the denominator. We can rewrite it as the square root of 3 over the square root of 4. And we don't want square roots or radicals in the denominator, so we have to do what's called rationalize the denominator. I guess in this case it would simplify to 2, but we shouldn't have fractions. There should be no fractions in the radicand, so you got to simplify those out. And then lastly, we have kind of a similar issue here. We have a binomial in the denominator, but one of those terms is a square root of 3. So we're going to have to do a process called rationalize the denominator by multiplying by the conjugate, which we'll see that in a later video. But there should be no radicals in the denominator. So those are things that we'll look for when we ask to fully simplify your answer. You'll have to hit those different things. Here's 2 properties of radicals that we've kind of been using before this, but if a and b are both positive, so positive numbers, then the nth root of a times b equals the nth root of a times the nth root of b. So basically we can separate them. So we've done this before. So say if you had like square root of 2 times the square root of 3, we can write that that's equal to the square root of 2 times 3. And then we could go both ways. We can go the way that I just went like that, or we could go this way as well. The square root of 6 you can rewrite as the square root of 2 times the square root of 3. That only applies if the index is greater than 1 and is an integer. So like 2, 3, 4, 5, 6, 7, 8, 9, 10. Another property, a quotient property of radicals for any real numbers a and b, where b doesn't equal 0 because it would be undefined. We have this property. So if you have the square root of a quotient, you can break it up into the square root of the numerator divided by the square root of the denominator, or the nth root. It doesn't have to be a square root. So those are some properties to keep in mind when you're simplifying properties of radicals. So let's simplify 1, 2, 3, and 4. And then as a try this, you'll do 5 and 6. So for number 1, when you're simplifying square roots, might help to do a little factor tree. So 72 would be 2 times 36. And you're looking for pairs. 36 is 6 times 6. So once you have pairs, you can square root, right? Square root 36 is 6. But the square root of 2 doesn't have a matching pair, so it's stuck under the radical. So our answer, we're going to have a 6 on the outside of the square root, and we're going to have a 2 on the inside of the square root. For number 2, there's kind of a 5 weighting to be used on the outside, but 54, we would have 6 times 9, and 9 is 3 times 3, 6 is 3 times 2. So we're looking for pairs. Since it's a square root, the index is 2, that index there. So we're looking for pairs. So we're going to pull a 3 on the outside. Let's write this 5 that's kind of waiting around to be used. We have a 3 on the outside that we pull out from square root of 9. And then we have a 3 times a 2 on the inside. That 3 and 2 came from this 3 and 2 right here. So our final answer would be 15 times the square root of 6. For number 3, notice our index is 3. So instead of looking for pairs, we're looking for triplets or triples. So when we write our factor tree of 128, we're looking for not pairs, but we're looking for triplets. So let's keep going. 2 times 8, need more space. 2 times 4, 2 times 2. Okay, so there's the prime factorization of 128 is 2 times 2 times 2 times 2 times 2 times 2 times 2. So we're looking for triplets. Here's a triplet. This would be basically doing the cubed root of 8. 2 times 2 times 2 is 8. And then here's another triplet. That's like doing the cubed root of 2 times 2 times 2, which is 8. And it looks like we just have one that doesn't have two others to go with it to make a triplet. So that's going to stay under the cubed root sign. So we're going to have the cubed root of 8 times 8 times 2. That 2, sadly, staying under there. So the cubed root of 8 is 2. The cubed root of another 8 is 2. And we're left with a cubed root of 2 on the inside. So this triplet right here, it matches that first 2, and this triplet is that 2 right there. So we would have an answer of 4 times the cubed root of 2. And be careful to remember the index, to include this index here as you're showing your work. So that was when we were looking for triplets. This next one, we're going to be looking for this index of 4. We're going to look for quadruplets. So when we write 96, we're looking for 4 identical factors. So let's see, that's 2 times 48, 2 times 24, 2 times 12, 2 times 6, and then 2 times 3. So we're looking for quadruplets. Since the index is 4, we're looking to pull out a 2 for those 4 2's. But then these factors don't have quadruplets with them, so they're stuck under the radical. So we would have an answer of, we're pulling out a 2, and we're left with a 4th root of 2 times 3, which is 6. So this would be our answer. If you'd like to try 5 and 6 right now, notice they have 3's as indices. And if you write those out now, when you get to Schoology to do your try this, you'll have the answers ready for you. Let's look at our last topic on this page. When you multiply radicals, multiply what is outside the radical, and then separately multiply what's inside the radical, then simplify. That's one approach. Or another approach is you could simplify inside first and then multiply the like expressions. So let's look at 7, 8, and 9, and then you'll do number 10. So earlier I showed you that there was this property, the square root of AB is the same as the square root of A times the square root of B. And we can use that property here, just kind of in reverse, since we're multiplying them. So we can multiply what's on the inside, 3 times 12. So that would be the square root of 36. So the answer would be 6. You could also think of it as the square root of 3 times 12 is 3 times 4. And then notice I have a pair of 3's. And the square root of 4, I know that too. So that would be 3 times 2, which is 6. A little more complicated, number 8. Again, we're going to multiply the stuff on the outside. So that would be negative 15. And we're going to multiply the stuff on the inside, which would be 24 times 20. Now, rather than multiplying 24 times 20 and writing out 480, since we're going to have to break it apart anyway, let's just leave it as 24 and 20. So let's leave it as that. And then instead of multiplying those together, let's break those apart. So 24 is 4 times 6. That's 24. Then 20 is 4 times 5. So I know that we can take a square root of 4 and a square root of 4. So if we have our 15, negative 15 that was out there kind of waiting around, we can do a square root of 4. Maybe I'll do it as blue. Square root of 4 is 2. And then a square root of another 4 is 2. And we're left with a 6 times a 5 under the radical. 6 and 5 don't have any common factors. We can't really simplify that anymore. So we can just multiply them. So this looks like 15 times 2 times 2 is 60 times the square root of 30. So negative 60 times the square root of 30 would be our answer. And let's look at number 9. Notice number 9, we have cubed roots. So we multiply on what's on the outside. So that's 5 times like a 1 is out here. So that's just 5. Then we have a cubed root of 100a squared times 10a. Now I don't really know factors of like cubic factors of 100. So let's just multiply these. Cubed root. 100 times 10 is 1,000. A squared times a is a cubed. So a cubed root of 1,000 actually is, if we're looking for triplets now, 10 times 10 times 10. So we could pull out a 10 and we can pull out an a. So that would be 5 times 10 times a. So the answer would be 50a. And we don't need absolute value bars here since we started with an odd index. How about you try number 10 as a try this? And I will stop this video here and start a new video next time.